Welcome to the iCANX talks and this week's ACS Nano Rising Star Lectures. We have a very exciting program for you and two amazing speakers. I'll be joined by Dr. Jing Tang from Stanford University and Professor Alice Zhang, our organizer and host of the iCANX lectures. This week's speakers, I should introduce myself. I'm Paul Weiss from UCLA, also the editor of ACS Nano. This week we'll start with Professor Prineha Narang from Harvard University. Professor Narang is in Engineering and Applied Sciences at Harvard. She's won many awards, including the NSF Career Award, the Moore Inventor Fellow, MIT Technology Reviews 35, the Young Scientist Award of the World Economic Forum, Forbes Magazine 30 Under 30, and the list goes on and on. She's an amazing scientist and engineer. She designs materials at the smallest scales using single atoms to leap to quantum technologies. And it's my very great pleasure to introduce our rising star, Professor Prineha Narang. Professor Narang, the floor is yours.
Thank you. I will go ahead and share my screen.
I will stop. Yep, very good.
Wonderful. All right. So, good morning and happy Friday. Thank you for being here. Well, I realize for some of you it's Friday evening, and I'm delighted that you're here to hear about predicting and controlling correlated light-matter interactions. Before I get started, I want to acknowledge that none of this would be possible without the talented set of students and postdocs who've worked with me over the past few years. Many of these students and postdocs have now gone on to start their own groups, and I hope that some of you listening here today will consider joining me in future. The work we do, I'm a theorist, I compute stuff, but I collaborate very closely with experimentalists who can verify some of these predictions that we make. And therefore, I want to acknowledge some of the collaborators I have across the world, and of course, the work that we've done with them in the last few years will be discussed in this talk as well. So I take a broad view of predicting and controlling quantum systems. When we think about quantum systems, it includes quantum electrodynamics, where you're actually able to talk about light-matter interactions where you can't separate light from matter. This is ostensibly going to be the focus of my talk here today. We think about correlated electronic structure methods that can allow us to describe these types of correlations. And that's incredibly important because conventional techniques in their standard issue format, for example, are frequently unable to give us the types of observables that we're interested in. Whenever we talk about a quantum system, there's the system and there's the environment. And this is where techniques from open quantum systems become indispensable in the description of these types of complicated quantum states. Finally, we're in 2021, and this is an era where we think about computation not just on very large-scale classical computers, and we're talking about now exascale computation, but also using small, imperfect quantum devices to also leverage those in our calculations. Okay, and so we design some of these algorithms. We think about the quantum, we also think about how you can actually come up with some of these hybrid algorithmic approaches. This is a complex way of saying that we develop methods, we try them on small scale systems, we also try and scale them to the biggest possible calculation that you can do today towards making amazing quantum technologies possible. That includes quantum networks. There's beautiful work in quantum networks happening across the world now, work in quantum computing, both in fundamental science and in industry happening in this space. And of course, when we think about quantum technologies, quantum sensing is a very natural application that falls out. All of these we've described in a fairly comprehensive chemical review that just appeared. It's in a special issue on quantum materials, and I hope you will take a look at it. So when I tell people we predict stuff and there are correlations and this is going to be incredibly challenging to compute, frequently people ask me, well, what's the one method you use? And there's perhaps an expectation that I have a single technique to rule them all. I'll just say that bridging across those length scales, thinking about properties of finite systems, systems that are maybe small clusters of molecules or atoms, and going all the way up to an extended system with a superlattice and many interfaces. Bridging across those length scales requires synthesizing methods from quantum chemistry, condensed matter, from quantum optics, and there isn't a single method that gets you across that entire range. So we think about ways of actually synthesizing these different methods in ways that perhaps have not been done in the past, so that we may be able to get well-known observables like potential energy surfaces, like these level diagrams, but also find new observables that we can predict that may be accessible using the kinds of spectroscopies that are just becoming available. There is remarkable work happening at various FDL facilities. A lot of interesting tabletop terahertz techniques have been released, and these are an opportunity for us from a theory standpoint to predict observables that have previously not been thought about. Towards that, let me give you an outline of my talk, and I know I speak fast, but hopefully we'll get through all of this before the chair kicks me off the stage. So I'll tell you about linear correlated light-matter interactions. Really, I'm going to tell you about polaritons and how we capture polaritons from first principles. I'll switch gears, tell you about some nonlinear correlated light-matter interactions, and hopefully get to some of these highly non-equilibrium states that I alluded to in my introduction. So correlations mean different things to people, and let me tell you what correlations mean to me, right? There are genres of correlations that are at the microscopic level, and these include, for example, the canonical electron-electron interaction. A lot has been said about it, a lot has been written about it, and there are many techniques that allow us to think about electron-electron correlations quite well. There are other types of correlations that are also important that become very relevant in descriptions of quantum matter, and those include the electron-phonon interaction in particular. The electron-phonon interaction, I'll just make a bold and potentially provocative claim here that without capturing the electron-phonon interaction, thinking about excited state and non-equilibrium behavior in quantum matter is fundamentally incomplete. Okay, so these are critical, absolutely critical to faithful descriptions of these types of systems. We talk about these in the presence of an external field, an external drive, and of course, with these very nonlinear interactions, it's natural to ask about nonlinear phononic processes that might occur, thereby getting us to thinking about various phonon-phonon diagrams. We think about these correlations in the types of methods we develop in the group towards describing correlated light-matter interactions. So that external drive for us today will be a photon field, and these can, by the way, be polaritons come in various flavors, and that includes plasmon polaritons. That includes essentially light exciting some of the electronic excitations in the material, so you start to see a collective dance of the electrons. It could be phonon-polaritons, where you're talking about the lattice essentially coupling to this optical field. Again, in the linear regime here, they're exciton-polaritons. So excitons, essentially quasiparticles in some of these low-dimensional chalcogenides in particular, are of interest. These exciton-polaritons can also form very interesting condensates. But those three are maybe the more popular kind of polaritons that come to mind. Slightly less studied are, of course, magnon polaritons and combinations of each of these polaritonic interactions. So some materials can host multiple of these types of polaritons. What's key about these polaritons is that you essentially cannot separate the matter from the optical excitation. So these truly become correlated light matter states. You describe the correlations in matter using all of the techniques I talked about and thinking about the interactions I diagrammatically and heuristically just described, as well as thinking about the photon very precisely. As we do that, you might say, well, you talked about correlations and how you would treat them on the matter side. Tell us a little more about the photon side. Well, here are the choices, and this is a theorist view of the world with light on one axis, matter on another, going from analytical to computational approaches. Now, there are techniques and approaches that allow us to think about the photon very precisely, but frequently, and these come from quantum optics and traditional quantum electrodynamical approaches that frequently treat matter as a few-level system. And that approximation runs counter to all of the stuff I just told you about how correlations in matter are incredibly important to describe excitations in these systems. On the other end, there are really, really awesome electronic structure techniques where the photon is in some ways included. A good example of this is the GW, the Green's function approaches that treat the quasiparticle optical excitations quite well. However, the photon is almost always classical. So we and a few others have been working towards approaches both in non-equilibrium Green's functions as well as in merging QED and electronic structure. Now, you can merge QED and electronic structure both formally. This has been done. This has rigorously been shown. I'm not going to show you those proofs here today. It's a little too early for me and perhaps a little too late for some people to see a very detailed, rigorous derivation here. But it should suffice that by showing formally that these can be merged, you actually have that same ladder of electronic structure approximations that now apply to this combined QED plus electronic structure case. That is to say that you can have QED plus Hartree-Fock, you can have QED plus time-dependent density functional theory, you could have QED plus coupled cluster, and that same parallel structure of various electronic structure theories and their complexity applies also to their QED counterparts. I'm going to focus on a case that is perhaps a little more relatable to experiment, which is QED plus time-dependent density functional theory, okay? So time-dependent density functional theory will allow us to then look at things like absorption and emission spectra and things that can be measured in the lab today. All right, so our physical system on the left, interacting electrons, nuclei. Nuclei is basically how we're going to include the lattice, the phonons. It's also how, by the way, we're going to implicitly include temperature in our calculation. So what I'm going to show you are finite temperature calculations, okay? And of course, we have the photon. Via a one-to-one correspondence, we arrive at a non-interacting equivalent of the same physical system. And this essentially, effective Kohn-Sham system it's a one-to-one map as long as you can find a good mean fields exchange correlation kernel. And here, good is a way of saying a mean field exchange correlation kernel that captures some of the behaviors of the physical system that you might expect. I want to acknowledge that this is an area where there's really a lot of work going on. Ahim Rubio, Antoine Georges, Sharon Ham-Schiffer, Eugene Demler, Dave Reichman, the list goes on. This is an area that is really growing as to how we actually take a complicated physical system like this and come up with perhaps not always an effective Kohn-Sham system, but come up with approximations that get us both the ground state as well as the excited state correlations. Excited states here are actually fundamentally very, very important, okay? And this is where TDDFT is, in some ways, for all its flaws, still a good technique because it gives us some of those excited states. You can get those transition dipole elements. You can look at those matrix elements, and you can actually, in some cases, even linearize this. So that allows you then to do more things than you'd be able to. And we've been able to do this both in the time domain as well as in the frequency domain. In the frequency domain, life is in some ways easier. You have an effective eigenvalue, the theta equation, and you can use that then to get both the changes from this strong coupling to the matter as well as what is imprint on the incoming photon fields. You can talk about, in this, because this is within TDDFT, you can talk about the impact not just on the ground state, but actually very high-lying states in the excited state manifold. Something that we've been able to show is that excited state manifold is actually impacted by coupling to the cavity. It's not just the first couple of excited states. You can actually see things happening all the way up, including in the pi star type transitions. We include loss. Yes, loss complicates matters. You might be familiar with the low Q, the low quality factor of plasmonic cavities, for example. But still, there are regimes of strong coupling that exist there. In particular, when you think about strong coupling of those to molecular systems, there is an interesting question there around coupling to single versus a collection of molecules, so how much of it is a collective excitation, and how does that interplay both with increasing the coupling and changing the dissipation. We have taken first steps towards answering those questions, in particular thinking about how the spontaneous, the enhanced spontaneous decay changes with increasing the amount of loss, and what would be the spectral signatures of loss in such systems. I want to take a step away from this very kind of computationally intensive approach to also offer a slightly more intuitive approach that makes a couple of more approximations, but still gives you really, really interesting information. Okay, and this is a technique that, together with my graduate students, Nick Rivera, and a former postdoc, Johannes Flick, he has now started his own group, both at the Flatiron and at City College in New York. We introduced a technique where we think about photonic quasiparticles, where you're essentially taking the system on the left, many levels, the cavities, so you basically have a very large set of virtual excitations of this joint system. You replace it with a few virtual excitations of this system. However, and this is somewhat essential to our ansatz, is this idea that the photonic vacuum modes, once you have this coupling to matter, are different than the modes in the absence of strong light matter coupling. So we have this very general ansatz that allows us now to think about a non-perturbative, okay? And the word non-perturbative here is important because most theories out there are treating these systems as a small perturbation on, say, their more equilibrium behavior, and we're really talking about things that are strongly non-perturbative here in strong light matter coupling. And so we do that. We can compare this, and we can actually benchmark this approach to tell you that, yes, if you had a simple perturbative theory, right? Simple perturbative theory, or even not so simple perturbative theory, going from regimes of no coupling to deep strong coupling, our approach, variational QED and exact numerical diagonalization, will continue to be able to describe this system across the no coupling to strong coupling regime, but perturbative theories will frequently deviate very strongly. In fact, I would call this very lovingly a major discrepancy. The fact that it not only deviates a little bit, but actually has the wrong functional form. So we think we have a fairly general way of describing these strong light matter interactions, both thinking about them from a QED plus electronic structure approach, as well as thinking of them from this different photonic quasiparticle approach. One of the key examples, right? So you go back to that picture I had of the various types of polaritons that are possible. One that we've been really diving into a lot are these phonon-polaritons. And they're exciting because they allow you to take polaritonics into the mid-IR. The mid-IR is an interesting spectral band, both from a technological and from a fundamental standpoint. It also has fewer losses than you would get in the visible or the near IR. And essentially, these phonon-polaritons provide a way for us to get extreme confinement of electromagnetic energy. And this is something that really strongly leverages 2D materials, strongly leverages various types of new nanomaterials that have been developed, and it brings essentially optical control to the atomic scale limit. So we've been considering these in their 2D form and trying to describe and also address this conundrum of how you can get phonon-polaritons even in true 2D layers. So this is towards saying, okay, if I have a true monolayer that is in some ways the extremest limit of confinement that I can think of, I cannot squish electromagnetic energy down any more than a monolayer. And I can also talk about how an emitter, for example, couples to that. So we have, this is one of my very few slides with equations, so please stay with me. We've introduced a universal parametrization of a conductivity of a polar monolayer. This is a fancy way of saying that I have a way of describing with just a couple of ab initio parameters the general behavior of a any monolayer that is polar, that might have the potential to host phonon-polaritons. I'm going to use this functional form to talk about a known system, hexagonal boron nitride, and I'm going to talk about how we've used this then to describe a system that is new and we hope will be synthesized, which is these monolayer perovskites. So in hexagonal boron nitride, we have conclusively settled the debate around why a true monolayer of hexagonal boron nitride has this dispersion, even though there is no LOTO split at the gamma point. This dispersion and the behavior going from a monolayer to a bilayer was subsequently measured together with a group of Dmitry Basov at Columbia. We have more recently now been looking at what happens if you, for example, have different stackings of HBN. So even if it's a bilayer, but it's stacked differently, turns out that you can get some interesting ferroelectric effects there. And also if there is, of course, and we and everyone else in the whole world is doing twisted systems. But what we're trying to think about there is how does a polariton tell you something about the new phases you create in these twisted systems? All of it comes down to a good description of these phonon-polaritons in 2D materials, which we can do from the approaches that we have developed. We can also talk about how, when these go into regimes of ultra-strong coupling, so not just strong coupling, but truly those deep QED regimes, say you have disks of these, how does, say, an external emitter couple to a single optical phonon or a phonon-polariton that is excited, and what would be essentially the equivalent spontaneous emission enhancement here. We've made some predictions that we hope will be realized by talented experimentalists in the near term. So hexagonal boron nitride, a lot was known about phonon-polaritons in these systems. A new system, right? Or not just a new system, actually a set of systems that we've been thinking about, inspired by this report in 2019 from Harold Wong that you can actually have a true monolayer of strontium titanate that can be synthesized. We thought, well, how about strontium titanate and other AbO3 perovskites if you could have monolayers of these? Pardon me. What types of phonon-polaritons could you get, and how would that allow you to take these polaritons into different spectral bands where you also might be able to access other emergent phases? And we've taken steps towards this, in particular, contrasting and looking at HBN with the behavior of these monolayers perovskites, STO, lead titanate. We've also looked at lithium niobate. Lithium niobate is interesting in its own right because it's a highly nonlinear material. It also hosts this interesting phonon-polariton. We think that combining the types of condensed matter phases that have been talked about conventionally in these AbO3 perovskites together with the polaritonics allows you to think about really new quantum architecture. So we're working in this field, and I hope that some of you will find this to be interesting. All right, so what I'm going to do next is I'm going to skip over some of the nonlinear work and go directly to the non-equilibrium and optically driven systems. This is something that we've been doing in my group over the last few years, and I'm really excited to talk about it because I think it has nice connections with the types of experiments that are being developed across the world. So when we think about nonlinearities in some of these systems, you can think about phononic interactions. In particular, there are these highly anharmonic phonon-phonon processes, different frequency ionic Raman scattering, some frequency ionic Raman scattering. You think about the Q3 and Q4 processes. These nonlinearities are all allowed from symmetry, as well as readily accessible using some of those terahertz sources and also, of course, some of the FEL experiments that I alluded to. So essentially, you can use various nonlinear interactions between the phonon modes to actually change the vibrationally excited behavior of solids. You can also combine this with some of the cavity work I just talked about. And a combination of those two things would allow you then to say, instead of picking a particular very nice phonon mode, I could also use the cavity to do some resonance matching that allows me to really directionally redistribute this vibrational energy across this entire solid, thereby enabling non-equilibrium quantum optical engineering of new states of matter, right? And this is exactly what we've been doing. This is work that one of my postdocs, Dominic Jurashik, has been leading in the group. He is soon starting his own group at Tel Aviv University this fall. So phonons are exciting, not just because you can go from one phonon mode to another phonon mode, but also because you can go via the phonon to actually couple to other orders in the material, right? So I can drive the lattice, right? And this is a very intuitive picture. I'm using my hands to describe it. One of the simplest things I'll do is that I change effectively the interaction of the lattice with the electrons. So I can use drive of the lattice to change the electron-phonon interaction fundamentally. And that has been done. That's been shown to actually change, for example, things like the superconducting order parameter in some systems. And there you would describe it using a combination of Eliashberg as well as Migdal theory. Instead of driving the electron-phonon case, you could use the phonon drive to also couple to the magnetic order in these materials. And a really good example of this is where we're using an electromagnetic field to drive, for example, the electronic degrees of freedom of the magnetic ions that then give you essentially this notion of ultra-fast optomagnetism, right? Now, instead of optomagnetism, everywhere you see opto, you can replace it with phonomagnetism because of this really, in some of these cases, there is a very strong spin-phonon coupling. And that can essentially allow you to instead of thinking about these optomagnetic or magneto-optical effects, think about phonomagnetic or magneto-phononic effects, right? And here we're talking about effective magnetic fields that can really make qualitative changes in the magnetic order. So we've been able to look at this for nickel oxide. Nickel oxide is the fruit fly of people looking at magnetic systems. We've also more recently shown that all of this, I'm sorry, I don't know what happened there. I somehow skipped a slide. There we go. That in fact, you can get some of these same effects in a new, not a new material. This is a material that's been around for a while, but one that hasn't been studied as much. These rare earth trihalides, including, for example, cerium trichloride, where these coherent phonon dynamics in response to, say, an ultra-fast and ultra-short terahertz pulse can actually give you very, very strong spin-phonon coupling and very large, giant even phonomagnetic effective magnetic fields, much higher than what you see in nickel oxide. So this area of ultra-fast as well as quantum optical control of matter is growing. This is an area that actually allows us to think about correlations in matter quite differently. And I encourage you to think about these correlated light matter interactions further in your own research if you can. And with that, I'll get us to our summary. I know I'm nearly out of time here. I told you a little bit about predicting various types of polaritons, light matter interactions, and they allow you to think about control of molecules as well as matter. And then I went into a little more about how you could actually use some of these same ideas from non-equilibrium control for essentially vibrational control of quantum systems. So using the lattice, you could control various other orders in the system. I'd like to thank support from the U.S. Department of Energy, and both in the form of QIS programs as well as in our Photonics and Thermodynamic Limits EFRC. I'm particularly grateful also to DOE for giving us computational time on various clusters, and to the Gordon and Betty Moore Foundation personally for supporting me. Thank you for being here, and look forward to questions during the panel discussion. Thanks again.
Thank you so much for that fantastic talk, as always. Let me pull up a series of questions that have come in from our audience. Let's see. Here we go. Okay. The first is from you at Sichuan University. Great talk. Thank you. Could you comment on metamaterials in light matter interactions?
Yes, metamaterials, of course, in itself a very exciting field in light matter interactions. So essentially, where you're combining various things like a superlattice or various nanostructures to have behaviors that each of those individual constituents wouldn't. So some of the same types of non-equilibrium control that I talked about, right, can actually be coupled with things like making a metamaterial tape, so patterning a set of resonators that you're coupling to that then you're using to control the condensate. Those types of ideas totally exist. In the simplest version of a cavity that I draw, I tend to draw something that looks like a Fabry-Perot cavity, but it could absolutely be some of these various metamaterial concepts that you're using to couple to the matter aspect here. So that's an excellent question, and I would love to pursue that further if that's of interest here. Yeah.
Mm-hmm. And the next question, I have to go down here, is from Apostle. How about that? Professor Narang, did you establish your own company leveraging the research? And if so, or if you're thinking of doing so, how?
Oh gosh, this is such a timely question. So yes, there is one company that spun out of my group, Alira O'Connor. You're welcome to take a look at it. And starting it was its own adventure. It's a story I could tell for some time, but it involves a combination of interest in translating the technology as well as having people in my group who are interested in following that technology themselves out from the lab into this big scary world of commercializing a technology. So it's the first that came out of my group, and there's a second that's being talked about now. So there's this is certainly a very timely question.
Terrific, congratulations. And the third question is, what theoretical or simulation tools do you wish that you had that would jump your work dramatically forward?
I think the biggest would be a way to, not with all these approximations, but with still computational tractability to be able to talk about these higher order electron phonon diagrams. So we've gone beyond leading order. We can go to some of the bubble diagrams, but there are many other higher order processes that we can write out. We have no easy way of saying that they don't contribute at lower order. And so I really think that there is an opportunity here to think about higher order electron phonon interactions where we have the equations, but ways that you can computationally implement them in a way that is efficient. That would be really, I think, a game changer in understanding these excitations in quantum matter.
Terrific. Well, this is the point at which we walk across the stage and I present you with a plaque thanking you for the talk and naming you the ACS Nano Rising Star, but we're going to have to put that off for a little while yet as the world reopens. But we're delighted to have you both give this iCANX talk and to have you associated with ACS Nano. And I know you've already been such a strong contributor. We really appreciate all your help and support and getting up early this morning as well to share your work with us.
Thank you. It's been a privilege.
Pardon?
It's a privilege, and thank you for having me here.
Well, we'll bring you back in just a little while after our next talk for a panel.
Got it.
And so it's my pleasure now to introduce Professor Lauren Zarzar, who's on the faculty of Chemistry and Materials Science and Engineering at Penn State, where she's off to an amazing start, having won an NSF Career Award, Packard and Sloan Fellowships, the Marion Milligan Mason Award of the AAAS, Army and Air Force and Investigator Awards, and many more. We're proud to have her give the iCANX talk today and also to join our ACS Nano Rising Star Board. Professor Zarzar, I'll turn the floor over to you now.
Thank you very much. All right. Yes, thank you very much for inviting me to participate in this. This is really wonderful. And I'm excited to be able to share with you
It's a bit hard to hear you.
Can you hear me if I sit closer to the mic?
Still muffled, I would say.
You can get close to your computer. I think that works.
Is this any better? I'm sitting pretty
Yeah,
close to the
better.
A little better, yeah.
Yeah.
Okay. If you want me to switch to my phone audio, I can try to do that. Is this okay?
Yeah, Laura, I
better,
think that's
yeah.
okay. Yeah.
Okay.
Yeah.
All right. Sorry about that.
Oh, no worries. Thank you.
Okay. Yes, I'm excited to share with you our recent work on exploring how to generate structural coloration from microstructured surfaces. And this work was done in collaboration with a number of fabulous people I've listed here, and particularly the simulations and the modeling was done by Sarah Nagelberg and Matthias Kohle at MIT, so I'll give them a lot of credit for this too. So when we think about mechanisms for generating color, most of the color that you see in your day-to-day lives probably comes from pigments and molecules that selectively absorb certain wavelengths of light while reflecting others. But there's also an important class of color-generating materials that all lump together under the term structural color. So I'm just going to show a few of these here. So structural coloration comes not from specific molecules in the material. The material itself might be entirely clear, like this soap film, for instance, but how the light interacts with the material, such as by optical interference generated by something like a thin film, a photonic crystal, or a diffraction grating, we're able to generate color through that light-matter interaction. And so, for instance, we have this bubble, which is colored through thin film interference. Opals have photonic crystals in them that generate optical interference. And many insects and butterflies that have these beautiful iridescent colors are also receive their color due to structural color. Now, typically when you think about generating structural color, we're thinking nanoscale periodicity in order to generate optical interference between wavelengths in the visible spectrum. So we were quite surprised to see when we were making these microscale droplets that they had quite a bit of color in reflection. You shine white light on these droplets and they had these beautiful iridescent colors. Now, these droplets are composed of two different oils, heptane, which has a refractive index of 1.37, and perfluorohexane, which has a refractive index of 1.27. And we make these droplets in microfluidics with this specified shape and size. Now, these droplets are obviously on the micro scale. There's no nanoparticles, there's no dyes. Everything is clear, and yet they had this beautiful iridescent color shifting property when we look at them under white light. So we were very intrigued by this. Where is this color coming from? So as good scientists, we dove in a little bit to try to figure out what's going on. If you take a look at these droplets under a microscope in reflection, what we see is that each of these droplets have their own color. So we see this colored ring, which is near the three-phase contact line of the droplet. So it's worth pointing out that these droplets are oriented vertically. So the substrate would be beneath the droplet here, and the colors coming from right above the heptane phase. So we see that the color is generated from single droplets, not from some long-range ordering of the individual droplets. When you change the size of the droplet, we also notice that the color changes. So here we have droplets that are all the same shape, but are different sizes, and that give these different rings of color. When viewed macroscopically, we have this silvery, glittery appearance because all of those colors are getting mixed up when they reach your eyes. So we wondered whether there was something special about the fact that these are liquid. And so we polymerized the droplets into solid particles, and indeed they retained their color. So this is not a property specific to liquids, but we do see that the orientation of the particle is very important. So in this picture, you'll see quite a few particles that are tipped on their side, and these don't generate the reflected color, whereas the ones that are sitting upright still have this colored ring. So putting together all of these pieces, we felt like what the important part here was actually this internal interface, this interface between the low index heptane and the higher index perfluorohexane. And so how can we remove all of these extra interfaces that might be complicating things, to just simplify this to the easiest system possible to deal with? And we came up with this, which is just water droplets, a water droplet of a similar contact angle and radius of curvature and size to the inner part of these oil droplets. We have the water, which is 1.33 refractive index, slightly higher than the air. So we wondered, is this going to generate the same optical effect as whatever is happening in our droplets? So we did an extremely simple experiment, and many of you have maybe even seen this yourself. We just took a polystyrene plastic dish, poured warm water into it, and put the lid onto the dish. You can see these beautiful colors that appear as the water condenses on the lid of the Petri dish. Now, this is a very common effect. I now see this in the kitchen. When I put Saran wrap over warm food, I'll see these colors. You may also see it in a water bottle on a hot day when you go outside due to this water condensation. If you look at this surface under a microscope, though, what you will actually see looks like this. So this is a picture of that plastic dish under a microscope, and we see these rings of color around each droplet, where the color appears to depend on the size, and very similar image to what we saw with the oil droplets. So based on this, we thought this is probably the same mechanism, but we need to explore further, in particular, what is causing this? So we needed to gain a little bit more information about the iridescent effect. So can we characterize that? Where are these different colors going? Oh, I apologize, I skipped over this slide. We were able to pattern the water droplets by patterning the different hydrophobicities over the surface. So there's water everywhere here, but only where the contact angle is high enough do you actually see the color, and everywhere where the contact angle is low, no color is reflected. So how do we explain where the color is coming from? Well, what we noticed was that we always have this refractive index contrast from high to low. So we can have a phenomenon called total internal reflection occurring, which is what happens when you have this high to low refractive index contrast, and at or above a certain critical angle, light actually reflects like a mirror. So this could be how light is getting reflected from the droplets, but it doesn't explain where the color is coming from. So we needed a method to be able to characterize the iridescence. And we developed this very simple technique. We often call it colloquially the ping pong ball method, where we put these droplets in a dish, and then we shine a small collimated light onto this surface. And then we place a ping pong ball, half ping pong ball with a hole cut in the top on the surface of the sample, and the reflected colors get projected onto the inside of this dome. And so now we can take just a couple pictures of this ping pong ball and be able to tell where the different reflected colors are going in three-dimensional space. So this is a really simple way for us to characterize the iridescence of the surfaces. So we just take a few pictures, maybe from the top or from the side, and then we can correlate these photographs with different three-dimensional coordinates to know what angles these colors are reflecting off of. And what we found by looking at this was that we had quite large angular separation between the various colors here. We have tens of degrees separation between the red, green, blue, etc., which was really interesting because when you think about, for instance, how an atmospheric rainbow works, this is one thing we were wondering, could this just be the same effect as an atmospheric rainbow? But that is due to dispersion and refraction, and you only get a couple degrees angular separation between the colors in that rainbow, whereas here we're having tens of degrees separation. So we didn't think that it was the same mechanism. There was something else going on here. To cut to the chase for how we eventually devised the mechanism going on here, what we realized is that we have optical interference occurring between rays of light bouncing by different paths of total internal reflection. Now, at the beginning of this story, I said when we think about generating optical interference, we think nanoscale periodicity. Here, we're having optical interference in structures that are on the tens to hundreds of micron scale. And this is possible because at these concave surfaces where we have light undergoing total internal reflection, there are multiple different paths that the light can take. Here we have a diagram that's just showing a 2-bounce trajectory and a 3-bounce trajectory. These trajectories have different path lengths. The light becomes has a phase shift, and then this leads to optical interference. And this is actually what's generating the structural color in these droplets. Now, we wanted to actually verify this, really, and develop a model to be able to predict the iridescent color in these surfaces. So we took a step back and we simplified things even more. Instead of a 3-dimensional surface, could we just devise this in 2 dimensions? So we only have to initially start by modeling light in a single plane. So a cylinder, a cylindrical segment, would allow us to do this. If you bring light in perpendicular to the length of a cylindrical segment, you have the light only propagating along one axis. So we printed these cylinders using multi-photon lithography and probed their optical properties. And in collaboration with Sarah and Matthias Collet at MIT, we were able to develop a model for this. So here's what the experiments look like. You see these reflected color bands from these cylinders in macro scale. If you look at these structures in the microscope and you actually focus at different distances away from the surface, you can actually see how these color bands evolve and change as you go farther from the surface. So we devised this model that could predict for a given geometry, refractive index contrast, and input light angle. For every output light angle, we could simulate an interference spectrum. So this would be the intensity of various wavelengths in the visible spectrum, which you can then take that data and convert it to a color in CIE space. So our eyes are not perfect spectrometers, so we have to be able to convert this spectral data to a color that we would actually see in order to compare it to our experimental photographic results. So when we do that and we compare the experiment and the model, we see pretty close agreement. It's not perfect, but it's pretty close. A couple of things, for instance, that this model does not take into account are light is light that's reflected by high intensity, but not necessarily by total internal reflection. And despite that this isn't perfect, we are on the right track. We felt like this was a close enough match that we could move forward to 3-dimensional surfaces. So now we're back to 3D. Think of this interface as a bowl shape. And unlike a cylinder, where light will only bounce along one plane, here we have a much more complicated system where light can bounce by potentially many different, if you think about slicing this bowl up into different planes, there are many different trajectories that the light can take in a 3-dimensional surface compared to the cylinder. But we still had excellent matching. between the model and the experiments here. So there's a lot of data to show here, but I'll walk through it. So in this left-hand panel, we have change in droplet radius. So photographs of each of the droplets that we looked at, the corresponding ping pong ball experiment, as well as the simulated model. I'll point out that in our experiments, you'll notice that we have indexed matched the aqueous outer phase to the heptane phase. So you don't actually see the top surface of the droplet here. It's still there, but you just don't see it. It's invisible. And that was to simplify this so that we didn't have to take into account any refraction happening at that upper interface. So we looked at change in droplet radius, we looked at change in illumination angle, and we saw pretty good matching here. We did actually measure the reflection spectra for a few different reflection angles, and we did find that our experiments matched pretty well again with the model. Here's some nice pictures showing effect of radius of curvature. So we just made droplets of the same shape but a variety of sizes, and you can actually see the evolution in these color patterns as you increase the droplet size. And a couple of nice trends that we find is one, that when you have smaller droplets, the color bands are wider, so there's larger angular separation compared to when the droplets are larger. These color bands actually become narrower and more closely spaced. And as we change the size, you'll also see that the colors cycle through, right? Their positions are not fixed. So if you follow this red band, as you go to larger and larger sizes, the red cycles towards the back and then will reappear in the front. So both the width of this color separation as well as the positions of all of the colors do change with droplet size. And here's some pictures of illumination angle, and you'll see how the colors actually rotate around the light source. And so when you have the light source here coming in from the side, most of the colors are on the back of this ping pong ball. And as you rotate the light more towards a vertical angle, they will become in a ring shape closer to the light source. Now we're using these droplets, which is really fun because we can actually change the droplet shape. Droplets are sensitive to balance and interfacial tension. So if you modify the surfactants that you use to stabilize the droplets, you can actually get the droplets to change their morphology, and you can tune this very precisely. And this video is just showing this dynamic process of these droplets changing shape when we add surfactant. So we used this to our advantage, and we can actually tune the droplets between all of these different morphologies and examine their colors. And so what we see is that for droplets that have a perfectly flat interface between the two oils, there's no color because there aren't multiple paths of total internal reflection to interfere. And when we have a double emulsion, so a sphere inside a sphere, we also don't see any color because the spheres don't support total internal reflection either. But for any of these open concave structures, we do see color, and the color pattern changes quite significantly with even relatively small changes in curvature of that internal oil-oil interface. So what we could do with this is actually pattern different structurally colored images in these oil and water emulsions. So this is a petri dish full of these oil droplets in water, and we use a photo mask to illuminate parts of these this droplet mat, if you will, with UV light or blue light. And we have a light responsive surfactant stabilizing the droplets. So when you expose the droplets to UV light, the surfactant will undergo a cis-trans isomerization. So basically it goes from being an effective to an ineffective surfactant, and this changes the droplet shape. So in this penguin image, for instance, we have two different shapes of droplets. There's one shape of droplet that corresponds to the blue color and another shape of droplet that corresponds to the green color. And this would be an entirely writable and erasable image. So my student had a lot of fun using different photo masks and patterning different images with this. Of course, the image doesn't persist forever because everything is liquid. And so eventually the surfactant will diffuse away and you'll get a washing out of these images. But this is a nice demonstration of just an entirely liquid system, everything's clear, we can actually begin to think about patterning structurally colored pictures in this. Now, more recently, we've been moving to solid microstructures. So we've been various methods for making these. For instance, these were made by embedding solid particles into a polymer film. So we can see, again, the same colored ring effect from each of these particles in the film. And it's by the same mechanism, except here we don't have a droplet. We just have two films with you could think of it having either a domed surface or a weld surface between two polymers, just depending on what index you have for each of the materials. So this is a way we're actually exploring making these in polymer films. So this is one of our early prototypes we have here, just looking at this in the lab. So you can see what these colors appear to be. We are in the process of trying to optimize this a little bit, make it more uniform, playing with a lot of different geometries. But the idea is pretty simple. All you need here is two different polymers that have a transition from a high to low refractive index, and you need some microscale interfacial geometry where the light can bounce by total internal reflection. So this is just one example of a geometry that we've tested that works, and just to give you a sense of what these design parameters might be. So once you have a solid surface that generates this effect, there's all sorts of fun things you can do with it. For instance, you can stretch it, it will change color. You can take wells and fill them with different liquids that actually change the refractive index. For instance, liquid crystals will change the refractive index where you go above and below the nematic to isotropic phase, which is what we're looking at here, so we can get a temperature-induced color change. You can pattern a liquid, a high-index liquid inside low refractive index micro wells, and actually use this to draw different patterns and structural colors. So that's what this video is showing here. We're patterning a high-index clear liquid into silicone wells, and to make this rose picture. So we used two different oils of two different refractive index, which gave us this colored image. We're also thinking about exploring different wetting phenomena and looking at, for instance, in this video, we have methanol that's evaporating off of the domed surface, and you can see how as the solution evaporates, you have these different color patterns as the liquid is drying across the surface. And so can we actually use this method to learn about microscale wetting phenomena or droplet shape, for instance? So just a few takeaways from this talk. We can generate structural color by interference, but we're using microscale geometries. And this is made possible when you have light undergoing multiple total internal reflections at a microscale concave surface. And there are only a couple requirements. You need a transition from a high to low refractive index. That's what's giving you the total internal reflection. You need some sort of microscale geometry where the light can bounce by multiple times by TIR and with multiple different trajectories. The surface does not need to be spherical. I know that I've primarily shown you spherical surfaces, but you can think about using asymmetric surfaces or polygon surfaces. And as long as there are multiple trajectories for total internal reflection that can interfere, you will get this effect. A few applications that we're considering pursuing with this include making paints, coatings, or cosmetics, security films, holograms, anything that has color shifting effects or color shifting inks that might be useful. Maybe displays as well as sensors. So if the color changes in response to a stimulus, that might also be an interesting sensing platform. So I'd like to thank my research group as well as all of my close collaborators on this project. And this research was funded by the NSF. And thank you all very much for your attention.
Hello.
Thank you so much. Sorry, it took me a moment. I was trying to get the last question in there. That was an amazing, amazing talk as always. And you've made so much progress as well since the last time that I was able to see your work. Let me pull up the questions here. There we go. So first, thank you, Professor Zarzar. Beautiful talk. Can you color by patterning on substrates or on particles?
Yes, so you can definitely pattern the color on substrates. For instance, you could, well, what we're thinking about doing is having different shapes or geometries of structures that you could then pattern over a surface so that you would get structural colored images. Particles might be a little bit trickier, but if you had different shapes or sizes of particles that gave different colors, and you could formulate that into an ink, you might be able to print that over a substrate as well to get color patterning.
And I'll read the other comment, which was also beautiful slides. Could you please give a talk on slide design?
I actually do, well, I won't, I know it's not exactly a question I can answer now, but I will say this is something that we think a lot about in my research group, and being able to design slides as well as figures that are visually appealing and also communicate effectively what you're trying to say. So I think it is really valuable to think about, and I appreciate that people care about this. I'm a big proponent of the black background.
They are striking. And this is, sorry, I didn't have a chance to edit it and correct. It was a question from Xinghua, substituted in for one that you answered during the talk. So can the solid microstructured surface coloration remain stable under extreme physical changes?
So if you change the geometry, you will change the color, because the color is a direct reflection of the paths that the light is taking at those interfaces. So if you're talking about extreme mechanical deformation, then the color is going to change in that case.
Mm-hmm. And then our third question is from XF Liu at Nansha University. How do you control the droplet and change the shape in liquids? And is it reversible? Sorry, I didn't get a chance to edit that properly.
Yes, so we do change the droplet shape, and we do this by adding different surfactants. I didn't spend a lot of time in the talk discussing what surfactants we used and how we do this, but we do have some other publications on that if you're interested in reading a little bit more. But we basically have this whole platform that we've developed for modifying the droplet geometry by mixing and matching different liquids in the droplet and different surfactants, and it is reversible. So if you change the surfactants combinations or concentrations, then the droplet will respond reversibly.
Fantastic. And again, this would be the time when we could walk across the stage together, and I could acknowledge that you're one of our rising stars at ACS Nano, and thanking you for this lecture. And hopefully very soon we'll be able to travel again and see each other in person. And I'm sure by then you'll have even more amazing science and materials to show us. And
thank you very much.
Oh, it was just wonderful. Oops. And now what we'll do is we will bring out our panelists, Dr. Jing Tang from Stanford University, and our organizer and host, Professor Alice Zhang from Beida. And so let's move to that point, and let's bring everybody out for this.
Okay. Hello, what a nice talk. Yeah, I really enjoy very much. Yeah. Paul, maybe I can first ask a question from the audience.
Please, yes.
Yeah. Yeah, the question is coming later. It's from Holland. So the Liz was asking for any possible to Lauren, for any possible to make this chip level and using this and write and rewrite.
I think that we can make inexpensive sheets of these because you only need, you know, 2 polymers, you need common thermoplastics, and this is something that we're exploring in terms of actually making and fabricating these in inexpensive films. The writing and rewriting part, that was in liquids. We currently don't have a good way to do that in solids, but if you were willing to have a liquid ink that was maybe dissolvable so that you could put a new one on, that might be a way to do it inexpensively.
Okay, very nice. Thank you.
Dr. Tang.
Okay, Paul, maybe we first welcome our challenger,
Yes.
Dr. Tang Jing, to ask some challenger questions.
Yes, please.
Thank you so much, Alice and Paul, for kind introduction. Thank you, Lauren and Prey, for your great talks. And congratulations on your recognition as ACS Nano Rising Stars. Lauren, since you just gave a talk, I want to let you have a little break. So my first question is for Prey. Prey, I know you are an avid triathlete and a runner. So I'm curious, how do you strike a healthy balance between work and other activities, such as sports or hobbies? Do you find it harder to justify taking the time away from your research?
Yeah, that's a very interesting question. And my approach to it has been to think that the time I spend outdoors, the time I spend doing some of my athletic endeavors actually contributes positively to the science I do. So I don't view it as a competition as much as a very synergistic process where I think, you know, I do the best science when I've had time to go ride my bike and not think about it sitting at my desk or standing at my desk. So I try very hard to have, you know, some clear boundaries around when I'm available and when I'm going to be doing something that involves, you know, being outdoors and may not be available for a call. And one of my philosophies here, both in what I do as well as the people I work with, people I mentor, is that they should similarly try and define those boundaries. So they should say, you know, there's a time where I'm doing something, playing an instrument, running, something that I care about, and that's going to contribute to the science. So please let me, you know, have that time to myself. So that's, yeah.
Thank you so much, Prey. I'm inspired by you. Now I'm motivated to practice more swimming and hiking. My next question is for Lauren. Lauren, this year I will be on the job market. So one of the challenges for me to find a new research direction for my future life. Therefore, I'm wondering, how did you find your new research direction in your lab, different from that of your PhD and postdoc advisors?
Right. An important part is being able to eventually distinguish yourself from your past mentors. Although, of course, everything that we do in the future is related to and inspired by what we've done in the past. And for me, it's always been about following where the science leads me and what's exciting. I gave a talk on optical properties. I have no training in optics. That's okay, right? If you're willing to just go where your science leads you and be curious, then I think you'll be successful. And so a lot of what we've done has admittedly been a little bit accidental, but we've followed the paths, and with good collaborators and hard work and creativity, I think you can use that to help distinguish yourself from others and do really excellent science.
Thank you so much, Lauren. I really appreciate your sharing. I feel that it is great advice when I write my research proposal. Doing science can be challenging and tough. We pursue crazy ideas, but it takes a lot of work to bring these ideas into realization. And sometimes I want to give up and very frustrated and struggling. So Prey, how do you excite your students when a project is very challenging and tough?
Yeah. Oh gosh. So, every time we start something new, I tell people this is not a path that I have gone down. So this is not, I don't know the outcome. And I, think of it as you're going to be going this path. Maybe you'll look to the left and see, something better than what I'd imagined going forward. And you should follow that natural path. Or you may run into a giant brick wall with cliffs on both sides, and that's gonna be not something I can predict. What I can predict is it's going to be an exciting journey, and that's really what gets me inspired to do the science, and hopefully also what gets people in my group inspired to do the science. But I try and also, when people are feeling like, oh, that reviewer was really mean, and we've all been in that situation, I kind of tell people, well, it's not personal. It's they're trying to comment on some aspect of the science, and sometimes they may do it in a less than articulate way, but let's see how we can best address these concerns. So that's really how I try and get people over some of the natural science obstacles that we face in the group.
Maybe let me interject for a second. How do you choose people for your group? I think many of the people in the audience are students who want to hear, how to come work with you, or such a star person in their own field. How is it you choose people who've been able to be so successful in these challenging projects?
That's how to pick folks that you want to work with. I guess I've been on both sides of that. How do I pick somebody that I feel like I'm going to do the best science being mentored by them, and how do I mentor somebody to do excellent science? One of the things I look for is that spirit of adventure, somebody who's there and says, I know X, I may not know all the other things that need to go into this project, but they're willing to kind of dive into it and have that idea that it's okay to not go into the project knowing everything, and that training or what you've taken in a formal course is only a small fraction of what you'll need in that project. So I really look for that both in applications as well as in my conversations with some of the students when we were talking about, is this a good project fit? Is this a good fit for the group? It's also something I look for when I pick some of the mentors that I worked with in the past.
That's great. Great. Yeah.
Yeah, I was just going to ask Lauren the same question.
All right.
Yeah, I really look for creativity is a very general term that's potentially ill-defined, supposedly, when it comes to science. But I think creativity is such a huge part of being a successful scientist. And it's not just about learning the equations and getting the A's on the tests and doing the math, right? It's about being able to notice when something is different or unusual, and being able to devise new research directions that nobody's been able to come up with before. So I look for people, as much as I can. I know this is difficult, but people who see problems in different ways, because I think if you can build a team of people who think in very different ways, that's going to be the best research team that you can assemble.
Okay, Lauren, may I ask the following questions? Actually, I think the creativity is really important for the peoples. And in your group, are you always encouraging students to do brainstorming, something like this? Yeah, you got different kind of students. Are you encouraging them, to like something brainstorming, always talking discussion, different way?
Yes, I love brainstorming. There are all sorts of creativity exercises, forced association, these kind of things, right? So I really think that creativity also is not something that's innate, but it's something that you can, to some degree, change and practice and improve. And this is something that I bring up in our group meetings and in discussions with my students frequently, and I pay a lot of attention to this, is make people aware of it, and also make people believe that they are creative, because if you think that you are creative, you will actually become more creative. There's an association. It's sort of like a growth mindset. So I try to be conscious of this and use this in our research.
Thank you very much. I think try to, get the people believe they are creative is a little bit hard, because like in China, many people don't think they are creative. Yeah, normally. Yeah. Okay. Very interesting. Okay, Paul, please.
Yeah. So I guess the question I always like to ask, and that I hope will be on the perspectives you write for ACS Nano, is what's next for each of you? What would you like to do in the next, say, 2 to 5 years in your field? And we can start with Pri.
Yeah, thank you. So I've really been thinking about how we can actually make interfaces to these nanoscale components, right? So some of the color centers, emitters, and ways of bringing various quantum technologies together using principles from nanoscience. And the way to think about this is that we're looking at, say a big superconducting qubit that needs to be coupled to a really, really tiny spin qubit. And you need to think about how do you actually create each of those interfaces, and how are they each going to operate at their own quantum limit. And that really is a good area for theory and experiment to work together. So that's something that I've been thinking about a lot. Of course, these ideas in cavity control of polaritonics, I think we've just scratched the surface. I think we're doing the simple stuff now. What kind of polaritons can you create? How can you drive it into strong coupling? I think there's so much more that will, various types of condensates, thinking about various spectroscopies, ways that we can actually use these polaritons in future. So I think that area is just kind of opening up. We're at step one of a long journey there. So I'm excited about both of those directions.
Fantastic. Count us in on the interface problem. and Lauren, in your laboratory?
So related to this structural color research, I'm really thinking about two pretty diverging directions. One is much more applied. Unlike Pri, I don't have much startup or entrepreneurial experience, but this is something that I'm interested in learning about as an academic, and in potentially being able to take this technology and actually turn it into a product that people would want to use. And then the other direction is much more fundamental, where now that we have this understanding of how light interferes in microstructures, can we use this property to probe microstructured materials and dynamics of microstructured materials in ways that were not before possible? For instance, can we use this to remotely measure microscale contact angles of microscale droplets and learn about wetting dynamics, or use it for microscale spectrometers? So we have some ideas for how to do this. So these are two very different directions, but we're trying to pursue both paths.
Fantastic. Well, let me thank you both and our challenger, Jing Tang, and of course our host, Professor Alice Zhang. We do have these electronic certificates, at least, to share with you for now, until we see you in person as our Rising Star lecturers, Professor Prineha Narang and Professor Lauren Zarzar. Thank you both for amazing talks. And, I can tell just from the change, I follow your talks whenever I possibly can, and seeing the changes in just such a short time makes me want to schedule you for some regular, like quarterly updates for all of us. And maybe we can do that through the journal. So send us your best work, and we'll encourage the audience to do the same. That was just such a spectacular morning, and lived up to every expectation that I and we had for both of you. So thank you so much. Next week, we'll have Mate in City, hosted by Alice and by Jagadish. We'll be back with our challenger, Yu Zhang. He'll be talking about soft robots. And that is our iCANX talk for this Friday. Have a good evening, afternoon, morning, day, wherever you are in the world. And we look forward to seeing you in person someday very soon. Be safe and well. Thank you.
Okay, thank you very much. And really enjoyable talk. I hope we'll have both of you come back again.